Moment area method. This is a method developed by Otto Moore and Charles Green back in 1873, and this is a semi-graphical technique for determining slope and deflection at a single point. We did some slope and deflection back in solids. We used double integration method. This is actually the exact same method. We're just looking at it differently conceptually. Theorem 1 of Moore and Green's moment area method is the change in slope between any 2 points on the elastic curve equals the area of the moment diagram between these points. So here I have a simply supported beam with an evenly distributed load. My moment diagram is going to look like this. Under this distributed load, my elastic curve is going to look like this. Remember, the elastic curve is the deformed shape of the beam under the load. So I know that the pin and roller are not going to have any movement. They're holding it into place. That's why there's reactions there. But the rest of the beam is going to want to bow down under that load. And this is greatly exaggerated so that we can draw all of our necessary points here. You'll see that I have a point C drawn on my diagram. So it's going to come down here. And if I draw a tangent line at C, it's going to look something like that. Now I can draw another tangent line at A, and what I will end up with is this angle between those two tangent lines, C and A. We represent this angle as theta C with respect to A. And I've said C with respect to A because I'm going from tangent line A up to tangent line C. If I was doing it the other way, tangent line C down to tangent line A, we would represent this as theta A with respect to C. Now what the theorem 1 says is that I can find this angle C with respect to A if I find the area under the moment diagram between C and A. So the area is equal to theta C with respect to A. The second theorem for moment area method is the vertical deviation of a tangent at a point, C, on the elastic curve with respect to tangent from another point, A, equals the moment of the area between A and C taken about the deviated point, in our case, C. So again, back to our simply supported beam that is going to have an elastic curve there and a moment diagram there. It says we can find this vertical deviation of the tangent line drawn at C. So I'm going to draw a very small one here because we don't need that tangent line too big. Tangent at C to a tangent line drawn at A. So it's going to be this distance right here. That's the vertical deviation of C with respect to A. And that distance can be found by taking the moment of the area between C and A, so that's going to be this blue shaded area, about C. So we're going to have a center point here. That'll be our distance x bar, if you will. This taken about C. Let's put this into practice. I have a simply supported beam with a 100 foot-pound moment at the middle C, and then another one at roller B. And I want to find the slope at A and the deflection at C using the moment area method. So the very first thing I'm going to do is draw the elastic curve, or the deformed shape of the beam. So this beam is being rotated to the right and pulled up by those two moments. So our elastic curve should look something similar to this. Now with the elastic curve, I can see the two components that I'm looking for. The slope at A, which is going to be a tangent line drawn at A, theta A, and then the vertical deviation or the deflection at C. So that's going to be this distance right here from my at-rest point to the point on my elastic curve. Now again, this elastic curve is greatly exaggerated. If the beam deflected this much, it would be a real problem. So how are we going to use the two theorems to get our answers? So let's look at points on the elastic curve where I know where they are. These are our boundary conditions. So remember, for a pin and a roller, we don't have any movement. So my vertical deviation at point B is going to be 0. So if I extend my tangent line at A out here, I have this distance that's going to be theorem 2, B with respect to A. Now why is that important? Well, if you look at my blue lines, you see here that I have a right triangle forming with the at-rest beam, the tangent line at A, and the distance theorem 2, TBA. And I can find theta A with the inverse tangent of TB with respect to A over 16 feet. And we're using small angle theory here because it should be a very, 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 very small deflection. So that means that this goes to TBA over 16 feet, and our answer will be in radians. To solve for theorem 2, I need to find the moment diagrams. And the easiest moment diagrams to work with are moment diagrams by superposition. So I'm going to draw the moment diagram by superposition, and I'm going to cantilever my system at A. If my system is cantilevered at A, that means I need to solve for reaction BY. Now that I have BY, I can draw my superposition moment diagram. So starting with BY, it's pushing up on the system, so that means the moment diagram is going to come up to a maximum value of P times L, which is going to be 200 pound-feet. Then I have my applied moment at B, and it is causing compression in the bottom. Of 100 pound-feet, and then I have my second moment that starts in the middle at C and it is adding an additional 100 pound-feet from C to A. So here is my moment diagram by superposition, and see, I have triangles and rectangles. It's much easier to deal with. TB with respect to A, theorem 2 is all the area on the moment diagram taken between B and A about point B. So for us, that's going to be the entire moment diagram. And we're going to sum the moments about B. And we continue with clockwise is subtracted and counterclockwise is added. Then our triangular load, 1/2 base times height times the distance to its centroid from B and this will be acting clockwise, so we're going to subtract it from the equation. I'll have my next rectangular area, which is 100 times 16, and the distance to its centroid from B is 8. I'm being lazy and not writing units here because I wrote them all in the first one. And it'll be going counterclockwise, so that is an added moment. My last area is a height of 100, because we've already used that first 100 in my long rectangle. It has a width of 8 feet, and the distance to its centroid from B is 8 plus half of 8, which is going to be 4 feet. It is also counterclockwise, so it will also be added to the equation. Theorem 2 TBA solves to be 5,333.3 pound-feet cubed. And you see I wrote it a little bit higher because with slope and deflection, the amount that it deflects is going to change based on the material type or the cross section. So I'm going to add those properties in here, E being the modulus of elasticity and I being the cross-sectional moment of inertia. And this will be our distance from a tangent line drawn at A to a point on the elastic curve, B. Now that I have that value using Theorem 2, I can plug it back into my right triangle equation that I created for the slope at A. And I end up with a slope of a positive 333 pound-feet squared over EI. Again, the positive sign makes sense with our assumption because it should be a counterclockwise rotation from the at-rest position, and counterclockwise is a positive slope. The vertical deviation at C is going to be a little bit more difficult because remember we can find the distance from the elastic curve to a tangent line. So that's going to be this purple value here, TCA. But I don't want that distance, I want the distance underneath it. But again, looking at our right triangle that we started with for theta A, we can use similar triangles to get down to this entire height, and I'm just going to call that HC. So our deflection C is going to be that entire height HC that we can find with similar triangles minus Theorem 2 taken from point C. And we can find HC by doing similar triangles from TBA. So HC over 8 feet is equal to Theorem 2 from B to A over 16 feet. And we find that HC is going to be 1/2 of TB with respect to A. We've already solved for TBA. That's the 5,333 from before for theta A. So let's solve for TCA. That's going to be all the area on the moment diagram between C and A. And we're going to take that moment about C. Now I've got a trapezoid here, so I'm going to break that up into a rectangle. And by the way, this height is 100. Again, solving for using similar triangles. And guess what? I've got 100 over 8 positive, 100 over 8 negative. So these two are going to cancel, which means I just have to worry about that little triangle on top, positive, and the negative moment rectangle on bottom. So we've got 1/2 base of 8 feet times height of 100, and it is acting at 2/3 of 8 from C, and it is going clockwise about C, so this is going to be a negative moment. And then I'm going to add 100 times 8, and its distance 4, and we find that Theorem 2 TCA is equal to 1,066.7 pound-feet cubed all over EI. All right, let's plug in our numbers. The deflection at C is going to be 1/2 5,333.3 pound-feet cubed over our material properties E and I minus 1,066.7 pound-feet cubed all over EI, and we have a deflection at C equal to 1,600 and 3 significant digits pound-feet cubed all over EI. And we ended up with a positive answer, which means we are deflecting up. Again, this falls in line with our assumed direction and our elastic curve. This time we're given a member that is pinned at B, has a roller at A, and 1 point load off to the far left. We want to find the slope at point D. So again, I'm going to start off with the elastic curve. It should be pushing down on the left. There's no deflection at A and there's no deflection at B. So that means this is going to want to bubble up and then come back down. And D is where I'm looking for my tangent, my slope. So if I were to draw a reference line here, that would be theta D. Theorem 1 tells me that I can find the angle between two tangent lines. This entire system is just made up of a whole bunch of slopes. There's no flat piece here. Well, there's going to be some flat piece between A and B, but we don't know where that is exactly. So I can draw a tangent line at B, and I can find the angle between these two tangent lines, in this case theta D with respect to B. Zooming in here, we have parallel lines. Remember with the parallel line rule that this little tiny angle here is equal to this tiny little angle here, which is theta D. So this is theta D. And this angle right here is theta B. Which we can find just like we did with the last example with right triangles. Let's zoom back out so we can get a good look at our picture. So right triangle, and extend that tangent line up. Just like we did the last example, we can find, in this case, TA with respect to B, point A with respect to a tangent line drawn at B. Remember from Theorem 1 that theta D with respect to D is theta D minus theta B, and we can find theta D then with Theorem 1 and then adding that theta B that we can get from Theorem 2, where theta B is equal to TA with respect to B all over 6 meters. Okay, so now we have a game plan. We need Theorem 1 and Theorem 2 combined to get theta D. In order to get those, we need to have our moment diagram. So I'm going to do, again, moment diagram with superposition. So there is our moment diagram. The first thing I need is dB. So theta dB is the area between B and D. So that's going to be this little filled in triangle here. And the height is going to be, which is 135. Therefore, theta dB is the area between D and B, which is going to be minus 1/2 base 3 meters times height 135 kilonewton meters. And that is equal to 202.5 kilonewton meters squared all over those material and geometric properties E and I. Next we need Theorem 2, which is TA with respect to B. So that is all the area between A and B. And we're going to sum those moments about A. So that area is 1/2 base of 6 meters times height 270 kilonewton meters times the distance to its centroid from A, which is 1/3 of 6 meters. And this is going to be going clockwise about A, so we are going to subtract it. Now that we have our two components, we can plug that into theta D. theta d is going to equal to theta dB, which is the 202.5 kilonewton meters squared all over EI. And we're going to have to use a little bit of creative license here. Okay, with the way that we assumed our picture, we can see very clearly that theta dB is going to be the summation of theta d plus theta b. So that means our equation here is going to change slightly with the magnitudes, that we're going to take theta b and subtract it from theta dB. So coming back down here, that's why I've left off the signs. So we're going to take the 202.5 and we're going to subtract my theta b, which in our case is the 1620 kilonewton meters cubed all over EI divided by 6 meters, and we get theta d to have a magnitude of 67.5 kilonewton meters squared all over EI. And putting my signs in here where they belong, we end up with a positive 67.5 kilonewton meters squared. If the peak of the elastic curve happens before D, we are going to have our tangent line at D here. That remains the same. And we'll still have our tangent line at B here. So we still have our theorem 1 here, theta D with respect to B, okay? Where this angle right here is theta D, and this angle here, I know it's small, I apologize, is theta B. So see, theta D is still going to be the difference between theta B and theorem 1 dB. This time we are given a cantilever member that is 8 meters long. The first 4 meters has a modulus of elasticity of 160 gigapascals and a cross-sectional centroidal moment of inertia of 6 times 10 to the 6 millimeters to the fourth. And B to C has a modulus of elasticity of 200 gigapascals and a smaller moment of inertia about the centroid of the cross-section at 3.5 times 10 to the 6 millimeters to the fourth. We want to find the vertical deviation of point C. So again, I'm going to stick with my game plan of starting with the elastic curve. And what's nice with a fixed end is a fixed end prevents rotation and translation. So that means it's going to come out flat here before it starts to bend down under the load. And what we are looking for is how far does C move down, deflection C. Here's what's great, is because there is no rotation at A, that means that if I draw a tangent line at A, it's flat, it has zero slope. So with cantilevers, my deflection at C is actually equal to theorem 2. Yay! All right, this is already fixed today, so let's keep it there for our moment diagram by superposition. So theorem 2, TCA, is all the area between C and A, so that's our entire moment diagram taken about C. Now here's the fun part. We have that change in material and cross-section at B. So I've got my purple zone here and my red zone. So let's start with the red, and we stop at B, which has a magnitude of 80 kilonewton meters. So taking just the red area, I have 1/2 base times height times the distance to its centroid from C, which is 2/3 of 4 meters. and that is going counterclockwise, so it's added. Now we'll move to the purple areas. We've got our rectangular area, base of 4, height of 80, and a distance to its centroid from C of 4 plus another half, so that's 2. That is also going counterclockwise. Then we have the remaining triangle, 1/2 base times height, and the distance to its centroid from C, which is 4 plus 2/3 of 4. And then I have my last triangle, the 120. So that is going to be plus 1/2 of base times height times the distance to its centroid from C, 4 plus 2/3 of 4. And remember, we have our two different cross sections and material property. So this is EBC and IBC, where all of this purple is over EAB and IAB. Okay, so that's why I'm sticking with my colors here. Combining all of our constants over our changing material and cross section, I get 426 2/3 for area BC, and then for area AB, I get 4,586 2/3 kilonewton meters cubed. Okay, now that I have my numbers here, I can throw in my E's and I's to get my final deflection at C. Plugging everything in, you see we have some unit problems. So let's get those addressed. All right, now all of our units should be in newtons and meters because a Pascal is a newton per meter squared, which means that we get our vertical deviation at C to be 5.39 meters down. That's a huge deflection. Definitely not small.